So in part one, I think I promised you guys some craziness. So here we go. It's not really all that crazy. But you notice is that the stick is hanging and all torques are in fact balanced because nothing's accelerating. It's not rotating one way or the other way. So all torques are in fact balanced. But it's balanced at 70. You might think, Dios mio, how are we balancing this stick at 70 centimeters with a 20 Newton thing only at 10 centimeters? With a mystery one clear over at the 10 centimeter mark over here, with 70 minus 10, well, that's at 60 centimeters. And what in the world is this 2 newtons? Well, that's the weight of the stick. Okay? And so the stick weighs 2 newtons. Well, guys, where does the weight of the stick act? Because there's mass of wood here, there's mass of wood, mass of wood. There's mass of wood everywhere here, guys. So where do you put the weight of the wood? At the center of mass, because that's what the center of mass means. The center of mass is the point where you can consider all of the weight to be acting, or all the mass of the wood to be at. Even though there's mass everywhere, by definition, the center of mass is the one point where you can consider all the mass to be at, of the stick. Not of this, because the center mass of the entire system of both masses and the stick is the 70. And I know that because it's balanced there. 70 is the center mass of the entire system. But that's not the question. The question is this unknown mass over here. So that's not what I want to know. I want to know the unknown mass. That means I have to know all the torques involved, including the torque created by this unknown. So I have to go back and find out the torques that are balanced at the 70 centimeter mark. So I have to do the 20 times the 10 centimeters here. The wood weighs 2 newtons, the whole stick. So that means it's 200 grams, 0.2 kilograms, weighs 2 newtons, is 20 centimeters away. But on the same side, which is the counterclockwise side, because it wants to rotate counterclockwise around this fulcrum right over here, wants to rotate like this against the clock, it's going to add to the torque for the unknown side, clear at 60 centimeters away from that. So as I set that up, I've got on the clockwise side, I've got 20 times 10 centimeters, or 0.1. I've got 2 newtons times 20 centimeters, or 0.2, on the other side. But on the same other side, because it's also counterclockwise, I've got the mystery force times 60 centimeters, or 0.6. Because that's 10 centimeters and that's 70. The difference is 60 centimeters, or 0.6. So I'm solving for that F. So the setup's going to look like that. Woo, isn't that messy? So this is the unknown, F1, times 60 centimeters, or 0.6. This is the weight of the stick acting at the 50. Because the 50 is on this stick is the point where all the weight of the wood is acting, the center mass of the stick. The torque is on that side, and that equals the only mass on this side. I see there's wood here, but remember, all of the wood acts at the center of mass. Not on this side, it acts at one point. Makes the math a whole lot easier. And you solve for your unknown, your F, and there it is, guys, 2.7 newtons. Ain't that grand? So that's the value of the center of mass. You don't have to worry about 3/10 of the mass of the stick to be here, 7/10 of the mass stick being over here, and how does that, is that a calculus problem, how that evolves with how the wood's acting on this side versus the 3/10 on this side? No. All the mass of the stick acts at its center mass, 2 newtons. Done. Okay? Makes the math a whole lot easier. Okay, let's do more fun. There's old Sam tightening a bolt. Well, that's not very hard. It says 15 times 10, right? There's old Johnny there. He's got 600 newtons sitting on a 1.5 meter fulcrum. Where must the buddy 450 Newton Mary move to balance that John's weight? Well, let's do both of those. There's old Sam, 15 times 0.1, that's 1.5 meter newtons. It's not that exciting. There's the old 600 times 1.5, and then 450 times, I don't know. So you solve for the D thing, 2 meters. Bam, boom. Not all that bad. Oh, I thought they're going to give us one harder one in there. Oh well. So this is a completely different kind of setup than what you guys are used to seeing. Because now look at this, guys. The fulcrum is on the wall over here. So what are our balanced torques here in this case? Well, guys, in this case, our balanced torques are this mass pulling right down over here versus this tension. Oh, I shouldn't have used the red. Pulling right up this way. I'm great with the mouse, huh? So, and there's your fulcrum. So that's a different teeter-totter, isn't it? So this is the clockwise torque right over here. And this is your counterclockwise torque going the other direction. So that's where the balance is. So not all torques look like a teeter-totter, because this time we're rotating around this axis over here. Now nothing's moving, so I know this tension times 10 meters has to equal this mass times 7 meters, because nothing's moving. It has to be balanced. So I have to change this mass to newtons, so 120 is about 1200 newtons. So I know 1200 newtons times 7 equals my tension times 10, and I solve for my T. Okay, so that's how I find the tension, which is a force in that string. It doesn't look like a teeter-totter, but it's the same kind of a problem. Instead of the fulcrum being in the middle now, it's on one end. And I have a lever, and this lever's longer here than it is here, but it's all a torque problem. I've got a force at a right angle here, I've got a force at a right angle here, all acting around a point of rotation right over here. Okay, and what is the force between the beam and the wall? Okay, well, we'll get to that one in just a second, but let's do the A thing first. So when we get to the force between the beam and the wall, that's just going to be a balanced torque kind of thing, or you'll see that's just going to be a balanced forces kind of thing. Because remember, if it's 120 down over here, not 120 kilograms, meaning roughly 1,200 newtons, a little less actually, because 9.8, not 10. And then the tension's pulling up. Well, the difference between those tells us the force, because not only are torques balanced, forces have to be balanced. So not only are we in rotational equilibrium, meaning all the torques are balanced, we have to be in regular equilibrium, meaning all forces are balanced. Okay, let me get my pen off here. Alrighty, let's see what we got going over here. Alrighty, so there's the T times 10 meters equals 120 times the 9.8, making it newtons, times the 7, and then we solve for the T, and you get 823. Okay, so that means we have, let me go back to my pen, and I don't actually use this one. Okay, so that means this is 823. Oops, I thought I was using my pen. So that means this was 823 newtons. It's not quite 1200 newtons. But since I have 1200-ish newtons down, 823 up, this actually has to pull up a little bit. Because that force plus that force has to equal the down force, right? Because nothing's accelerating up or down, all forces have to be equal. So that's how we're doing the B portion down there. Okay? So that's what the B is asking over there, is that since this is less than the 1200 because on the longer lever, this actually supports some of the weight as well. Not as much because it's closer to this side than that. So that's why this side is going to be a higher force than over here. It's going to support more of the 1200 than that side. Remember, it's a little less than 1200. I don't remember what it was. Okay? So the actual force over there, it's not quite 1200, but it's 353. So this force plus that force equals this force down, which is a teeny bit less than that because, remember, it's 120 times 9.8, not 10. Okay? So that's how we do that kind of a problem. Alrighty, so let me Erase all ink on that slide, and let's carry on. Oh, here's another one. You might say, oh my goodness, I don't see a fulcrum on this. So consider the 400 kilogram beam as shown. How do you find the tension on that side? Well, if you want to find the tension on that side, the secret to this is you actually can put your fulcrum wherever you want to. And so where I would choose to put my fulcrum in this case is right over here. The reason I'm going to put my fulcrum here, I'm going to pretend that it's going to rotate around that point. I can choose that point. I could have chose the point on the right, but I'm trying to solve for that T of R. Since I'm trying to solve for that T of R, I don't want to put the fulcrum over there. So I'm going to put my fulcrum wherever it's handiest, and it's actually handiest right over there. Because now I've got this force or tension right over here. I've got that force times this lever arm, which is 7 meters. And that's being balanced with the entire weight of this beam, which is about 4,000 newtons. But where's it acting? So I've got the TR, so this is about 7, so it's 10 meters for the whole thing, 7 meters for there. So for the counterclockwise torque, I've got the tension on the right side times about 7 meters, and that's all the counterclockwise torque. Sorry for my sloppy writing there. That's the TR times the 7. Then that's going to equal my torque on the clockwise side, which is this side. And that's the weight of this thing, the mg, the big M and the G. But what's the distance on this thing? Well, the distance on that thing, since that's 7 meters, that means this is 3 meters over there. And that's 5 meters to the middle. That means this is actually 2 meters long, right? So that's times 2 meters. And since this is 400, so that's basically 4,000. So 400 times 10, so that's about 4,000 newtons times 2 meters. So that means that's about 8,000 meter newtons. Sure, we're going to use 9.8 when it calculates it and shows you this. So that means that this torque is also 8,000 because they're balanced torques. Nothing's moving. It's static equilibrium, meter newtons. And now you just solve for the T of R. So it's a teeter-totter problem, but now we're teetering around the left side. And you might say again, how did you know to put the T of L over there? Because the problem did not ask for the T of L. If the problem asked for the T of L, I would have put the fulcrum over there and solved for the T of L and done it that way. But it didn't ask for that. It asked for the T of R, so I need to solve for the T of R. That's why I put my fulcrum there. I can put my fulcrum wherever I want to, guys. But I want to put the fulcrum where it makes my problem the easiest. And it made my problem the easiest because I don't know what T of L is. And there's no torque there. If I put the fulcrum at T of L and I don't know what that tension is, there's no torque there if I put the fulcrum there. There's no lever distance there. So it makes my problem easier. So when doing some of these problems, it's just figuring out where to put your fulcrum to make the math the easiest. Okay, so that's how I decided where to put the fulcrum. Alrighty, so let me get rid of all my stuff there, erase all ink there, and they'll show you the magic there. So that's what I was just talking about. There's the weight of the thing, 400 times the 2, and that's the torque on one side, which is a little less than 8,000. That equals a TR times the 7, and wait for it, bam, 1,121 newtons. Okay, there you go. Pretty exciting stuff, huh? All right, let's get to some muscles. Alrighty, so if we want to look at inside the body, because some of you would like to be doctors one day. Oh, we're about out of time, so we're going to take a pause and we're going to finish this muscle thing on part 3. It'll be exciting. Alrighty, see you in part 3.